Hello everyone, welcome to QCon Plus 2020. I hope everyone is healthy and comfortable today. In my session, I will introduce you to some cool data infra challenges that you only see in IoT space. Let's start with a small problem that you might relate to. Tesla designed a supercharger network to enable a seamless, enjoyable road trip experience. It can be quite frustrating to drive to a supercharger only to notice that it's down. So we provide real-time visibility into superchargers' health status. We receive telemetry from our superchargers that let us know when a post is occupied and various other stats. Using this data, we can assess the health of a supercharger. Now on the surface, it's a tractable problem, but there are many edge cases which make it novel. Some issues such as a broken connector or an obstructed parking stall will prevent the vehicle from charging through that supercharger post. And in some cases, the supercharger may be perfectly healthy, but due to extreme weather or some other reason, it might lose connectivity with the cloud and stop sending telemetry. So the down detection algorithm, the algorithm which figures out where to route a user to, has to employ many heuristics. It has to not only be ready for the superchargers which are sending data in a perfect way, but it has to also account for the fact that data can be missing many times. While any algorithm which depends on data has to be prepared for missing data, but in case of IoT, it's not a rare event. It's actually quite common. It's problems like these which make IoT data space very unique to work with. My name is Shrijeet. I'm part of core data platform team at Tesla. My team is responsible for handling all mission critical data systems at Tesla. And today I'm here to tell you more about these unique challenges and some unique solutions. Let's start with a 10,000 feet view of IoT data pipeline. Most of the devices, at least in case of Tesla, run a Linux operating system and provide local data storage, computation, and control while maintaining bidirectional communication with the cloud. The communication flows through an edge gateway that handles connectivity as well as security. The edge gateway integrates with the cloud, which has a Kafka cluster behind it, to ingest large volumes of telemetry. The Kafka-based PubSub provides message durability. It decouples producers of data from the consumers of data and allows sharing this telemetry across many downstream services. At first glance, the picture that we just saw, it seems very similar to any other data pipeline we can imagine. And the very first comparison that comes to mind is clickstream. The data that we collect from ad networks, the Googles and the Facebooks of the world. And we have come a long way in defining elegant design patterns for dealing with massive scale clickstream data that we observe at conventional internet systems. These design patterns work really well because the underlying data producer is stable and it is built with a common standard set of assumptions. You expect the network to be always reliable. You expect the traffic patterns to be more or less the same. And even if they change, even if there is a seasonality, after a period of time, even that can be predicted. Essentially, you trust the upstream to always behave well. And the way you make sure that they behave well is putting multiple layers of redundancy. A conventional software service is deployed in data center, which is responsible to make sure this redundancy is there. In contrast, for the most part, IoT devices are installed in a very hostile environment. In IoT, data acquisition can go partially dark for legitimate reasons, and thus knowing whether it's a real problem is very subjective. IoT devices generally suffer from lack of resources, power, storage, etc. Their computational and storage capabilities do not allow complex operations such as sanitization, putting a standard format, deduplication, and things like that. And finally, like I've been repeating, intermittent loss of connection in case of IoT with the cloud is relatively frequent. IoT devices are also incredibly heterogeneous. regarding basic communication protocols, data formats, and technologies. Furthermore, in case of IoT, if we divide data in two categories, one is diagnostic data, and the other category is something that is critical for the functionality of the device. The diagnostic data is always collected in best effort mode. And devices will choose to stop sending data if it comes in the way of providing critical functionality for obvious reasons. With its unique challenges, IoT data engineering has modest overlap with conventional approaches. Over the years, we have developed a few targeted patterns to undertake these challenges. Let's look into some of those patterns. The very first design pattern we use is isolation. We confine data pipelines along multiple dimensions. The obvious dimensions are business units. In case of Tesla, we have end-to-end data flow for every business unit. The underlying infrastructure on which these data flows run, that might be shared. For example, we might share Kafka cluster, we might share Kubernetes setup, we might even share some databases at infrastructure level. But at application level, they are completely isolated. The next dimension, the obvious dimension to divide after business unit is products. If we have multiple product models, for example, if we have multiple models of vehicles, they all will have their own end-to-end data flows. We'll not mix data from model A with model B. The next dimension at which we isolate is geography. And those were some of the obvious dimensions. And then there are some interesting dimensions such as transmission modes. Devices collect data periodically, and that's an obvious transmission mode where they're periodically sending some payload to the cloud. And there are cases when you would want out-of-band collection of data. For example, a service technician wanting to know more about your device, and they can request an ad hoc pull, which can be more verbose. So that's another place that we would not want periodic collection to interfere with out-of-band collection. While this strategy of isolating pipelines and data flows across multiple dimensions allows us to limit the noise and allows us to reduce the problems of noisy neighbors and subsequently improve the data quality, the downside is that we have too many data sets and too many data pipelines to manage. The next commonly used pattern is deferred complexity. As noted, due to constrained resources, the devices cannot handle operations such as sanitization, putting some standard format. I keep saying standard format because, as noted, the data in many cases is proprietary. Deduplication is another thing that devices will never perform. They will always defer all these complex operations to the cloud. And the device is always operating in a mode where it can push as much data as possible, as fast as it can, and in the tiniest possible payload that it can manage to send that data. Now, on the cloud side, on the cloud platform side, to contain the heterogeneity and bustiness and noisiness of data, we try to explode the payloads that we receive, which are typically batched payloads. We get telemetry in batches. We try to explode regardless of which business unit or product this data is coming from. We try to employ some common strategies so that we can put sanitization, common standard formats, and some other standard cleaning steps in the first step of data collection itself. And this slide is a demonstration of that. As you zoom in into the Kubernetes magical black box that you're seeing there, that is running some real-time data pipelines that we have developed over a framework called Akka. We call this whole product Kafka channels. And in there, we apply these complex operations as the first thing as we receive these payloads. When you zoom in further in any given sanitization or cleaning data flow, subflow, you will find more subflows. And this pattern results in data processing broken down into multiple intermediate data sets and sub-pipelines on the cloud platform end. So we already had too many data sets and too many pipelines to manage because of the isolation that we were doing. And now due to this breaking down data flow into subflows is increasing this data sets and data pipelines even further. Our design choices and tooling has enabled us to digest the explosive growth that we have seen. And the patterns that I just described were instrumental in making sure that we are able to keep up with the growth. But the ease with which we can set up a new pipeline today was biting us back by making it next to impossible to keep a clean model in our head about data pipelines. And we had a fresh set of challenges around operating these pipelines and how visible the health of these pipelines were. So let's look into those fresh set of challenges as next thing. With the explosive growth, data sets under management kept growing, like I said, and the common way to organize that information is documentation. But the kind of growth we were seeing, documentation was not keeping up. The other common thing that you see in any data platform, in any company, is any data org is you have data heroes, data champions, which are your go-to guys for questions when you cannot figure out where the data is or where a particular piece of information is. And we also had them, but obviously that's bad. That doesn't scale. Beyond the number of data sets and the isolation pattern that we described, it was actually worsening the problem further. For instance, a device has many sensors, and some of those sensors may be perfectly fine, and they're sending data. We are collecting data end to end without any problem. But there could be some sensors, or there could be a subset of sensors which have stopped sending data, and that is also not a rare scenario. So in the context of data discovery, a user cannot just ask where is the data for device X or where is the data for a certain category of devices. A more pointed question, a more common question is where is the data for device X of kind Y? And then you throw a dimension of region, for instance, where is the data for device X of kind Y from region Z? And then you throw more dimensions and you can see how data discovery gets more and more complicated. The next problem we were seeing was governance. We required, since day one, developers to apply data sets and data pipeline changes through pull requests, which was great. And the build process could apply some elementary checks, whether syntax is correct, whether you're putting configuration at the right place or not. However, we relied on the human, the person who's looking at the code, reviewing the code, to spot data governance gaps such as regulatory requirements, data security concerns, naming conventions, etc. Over time, such processes add toil and they reduce to mere formality. What we wanted was the build to do all these semantic checks as well. Next, uncertainty, erroneousness, and noisiness is given with IoT data. We never expect 100% coverage at any given point of time. Like I said a few seconds ago, a device sensor for the same device, some sensors could be sending data while others might fail. So the coverage tells you that you might have some data available, but is it 100% or not is what you're trying to get from the coverage question. And we had some handcrafted metrics that would give you a sense of data quality, data coverage for some products, but we didn't have anything that generalizes well across all business units and products. And that was very important over a period of time, that we can confidently give an assessment of what is the coverage of our data sets. For a real-time data pipeline or even batch pipeline, data freshness represents the most important service quality metric that you can have. And for as long as I can remember, freshness was the single metric that we alerted on most accurately. It is simple yet effective for all parties involved. Data producers understand it, data consumers understand it, data scientists understand it, everyone understands it. And it's after a period of time, once you figure out the nuances, it's actually pretty easy to calculate. And we had some great tooling to calculate latency for individual steps. However, for someone at the far end of the spectrum, like a data scientist, for them, the data flow starts at the device and it ends at some data set that they want to query. Anything in between is implementation detail for them. They do not care how long it took for any sub-step. What they care about is what was the end-to-end latency. And we didn't have a way to expose that. So something that we were really proud of, we thought our service quality indicator in terms of freshness are great. They were actually not that great. So we covered some problems. We covered problems related to coverage. We covered the problem related to freshness. We didn't have a good story for governance. We didn't have a good story for data discovery. We decided to solve these problems through a tool chain that we now call DataFlow. And my next section is going to cover our solution. Data discovery is not a new problem. You might have that in your team, and you might be using some existing tool or infrastructure to solve data discovery problem. The way you solve, like the most basic solution for this data discovery problem is to have a catalog where your data sets are tagged with some kind of labels. And when you think about tag, you have two choices. You can have free text tags where a user can go to some UI or through some configuration and they can apply some any possible any logical tag or any combination of tags that you can imagine. That is free text tags. And the second choice that you have is you restrict the tags to a taxonomy. We chose B. We restricted the allowed tags to a taxonomy that we maintain in source control. And the reason we did that gave us some consistency. Now, as a platform engineer, we had little control over how owners curated these datasets. Beyond laying best practices, we chose not to dictate their names, schemas, etc., as that would restrict the expressiveness of the data owner, which is not great. We have an example here. Imagine you have a company which has two business domains. One is dealing with cameras. There's a thermostat business domain, and there are a few regions in which they operate. Each business unit has some products some product models that they're selling. Then typically in an IoT infrastructure, you divide the deployed devices into few categories. You can have customer category of devices. You can have prototype or engineering category, so you can test your devices. And then I explain the concept of publishing mode or trigger mode, periodic or out of band. That can be another dimension at which you want to tag data sets at. And finally, you can have data types. So although this is sort of a made up example of taxonomy, but the structure is pretty real. That is what we do at Tesla. We allow business units to have flexibility in the set of values that allow in certain dimension. You can have any number of products you want, and you choose to call the products whatever you want to call them, obviously. But each business unit has to have all these dimensions. They are common. Everyone has to have region, product, fleet, triggers, and data types. And combination of this is naturally hierarchical. If you take these files and put them into a single data structure, you get a tree. What is a path in tree? A path in this taxonomy, hierarchical taxonomy, represents a label. So you can take any path in the tree. As long as that's a valid path in the tree, we allow that to be a valid label. Imagine that there is a data set which represents data for a certain model of camera in the engineering fleet, and data is being pulled manually in that data set, and the data type in the data set is of telemetry kind. Then we can use that example taxonomy that I just showed you, and we can slap this label in. It can live, this data set can physically rest in multiple data sets. You can have some Kafka topics in which this data set is present. You can have you can have a random access database in which data set is present. You can have some batch database in which data set is present. Logically, they're all same. And so you can slap a single label, and that would be your logical data set. Let's take a pause here. So we have defined the concept of taxonomy. We have defined the concept of logical data set, and we are getting towards a solution for data catalog, which is great. All we need is some way to, given a label, we need to figure out what all data sets are covered in that data set, which is easy, right? But the other problem we had was around operability. How we operability and visibility. How do we deal with the number of pipelines that we had. How do we figure out what is the end-to-end latency? So we needed some data lineage abstraction. We wanted to capture the flow as data is moving from one data set to another data sets, all the steps involved in some abstraction, and that is data lineage abstraction. And we decided it would be prudent if you can combine data catalog and data lineage into one single abstraction. And that abstraction was graph. So we came up with the concept of DataFlow graph. DataFlow for a device sensor begins at that sensor as the origin and ends at a dataset in one or more data stores. As noted earlier, we break down the flow into multiple intermediate datasets and subflows. Data lineage captures this flow from its source to its destination via various changes and hops on its way. How the data gets transformed along the way and how it splits, converges after a stage. Naturally, it is best represented as a graph. If it is a graph, what are the vertices and edges? Each dataset, a physical dataset, for example, a Kafka topic in some proprietary format, or a Kafka topic for the same proprietary format in canonical format, like a standard format, in our case that is Avro. Then same data in let's say a time series database, and same data set in batch database. They all become data set, the vertices in this graph, and they're all labeled with same taxonomy label. I have the structure of data set in this slide. It has a name, it has a data store in which it lives, then it has a collection of labels, and finally it has a tier. The concept of tier is used in our case to organize our alerts. So we have we have defined how we capture vertices. Let's talk about edges. We represent intermediate steps as data flow steps. These steps are Kafka streams or batch jobs powered by Spark or MapReduce. A single data flow step can consume multiple data sets and produce multiple data sets. Hence, it can translate into multiple edges in the graph. We represent edge as data flow transformation. So data flow transformation has the step which produce this transformation, and then it has the tuple, the source and target data sets, which are involved in this data flow transformation. So we have defined what it means for vertex to be in the graph and what is an edge in this graph, but how do we put the graph together? In any mature data platform, after a period of time, you will find there are multiple frameworks involved. You might have some streaming technology, you might have some batch frameworks involved, and you will also have multiple storage technologies involved. In our case, we have Kafka, we have HBase, we have HDFS. And the configuration, how do you create a new topic? How do you create a new table in time series database? How do you create a new table in HBase? How do you create a new table in HDFS? It's entirely possible for those things to live in various different ways. You can have a team which is completely operating in cowboy mode, where they go to a terminal and just create the table there, or you can have more disciplined team which is writing tools which can read configuration and create these data sets and data pipelines for you. Even if you have everything in the configuration file, then this information can be spread into multiple repositories. And the problem with having this staggered information is that it's very hard to create what I just described, because you need to pull information from multiple sources and put it into one place. Luckily, in our case, even before we started with DataFlow, I've said this before, one of the good things that we have been doing is every change goes through source control. So we didn't have a problem of someone doing something random directly in production. And we just had one repository. We use a mono repository that we build using a build tool called Bazel. And Bazel organizes build rules in a simple configuration where you can feed in the sources, the source as in the code source, and then you can kind of chain the dependency graph. So this example is a very high-level example of how we actually do it. So we define a file group called Dataset, in which we feed all the configuration files which configure dataset into all different kind of databases that we have: Kafka topics, HBase tables, HDFS tables. And then we have a file group which captures all the data pipelines. We have the real-time data pipelines that we build, that we run, operate through a framework that we build called Kafka channels. Then you can also have MapReduce jobs and your Spark jobs in this file group. And then both those are fed into the final rule, which is the graph generating rule as dependencies. So if anything changes, the final rule will re-trigger and it will regenerate the graph. And Bazel captures this dependency and change detection very cleanly. Another thing to notice is we are not storing our catalog and lineage into any fancy database. Even with thousands of data sets and thousands of pipelines, this information, when serialized as data structures, can be stored in kilobytes. So what we have is a binary representation of our catalog and data lineage that we can supply to any downstream tool or any downstream service that wants it. And it regenerates for every pull request, so that we can now apply strong semantic checks as well, which was one of the problems that we had. We can verify that there is a data set A and data set B, and they should never be connected in any scenarios, because a data set A can have some private data that we do not want to make it to an openly accessible data set B, and that check can be put into the build stage. Now, taxonomy and graph give us a foundation for operating the telemetry pipelines. Next, look at a building block, which gives us some hold on visibility. And the common gist of visibility is that you should be able to monitor the health of a complex system by just looking into inputs and outputs of the system. We described that freshness is a very strong indicator for figuring out the service quality of data pipelines, but there are problems such as coverage and completeness which go beyond freshness. And how did we solve them? Measuring data quality requires looking at data in aggregate and identifying patterns rather than individual events. The rate of individual events that we see is about 30 million events per second. That is the peak rate. That translates to trillions of events per day. And if we had to go and infer data quality, it's perfectly doable, but that is very expensive in terms of cost, computation cost, and it is prone to lag. Now, if we take a step back and think from first principle, what is needed to for example, derive coverage? For every payload that we receive from the device, if we can record the fact that we received the payload at certain time, next, if we can associate that payload with a device ID, and finally, if we can associate and record where we actually received that payload, with these three pieces of information, we can actually do very interesting things. Let's take all of these things and capture that as a meta record called trace record. And that's what we do. We have a concept of DataFlow trace, and a blessing in disguise is in case of IoT, data always comes in payload, and the payload rate is actually not a lot, maybe a billion per day. When we explode those payloads, when we process those payloads, that's when we get into 30 million per second kind of throughput. So we record traces at raw payload level, and we store those traces. Every payload that moves, the very first entry point records that we received something at this data set at this time for this device, and we take that and store that as a separate metatable. And by analyzing that metatable, we can do very interesting things. For example, coverage. This is a dashboard, a real dashboard, which gives us a sense of coverage for any given product and transmission mode for across all business units. It's a very general solution. I'll explain this dashboard pretty quickly. So for every transmission mode, whether it's pseudonymous, urgent, or manual in our case, we know the number of devices which are expected to send data. There are like about 790K devices which should be sending us data. Then for a fixed period of time, daily, weekly, and monthly, we know what devices are actually sending us data through tracing. And then we once we have these two pieces of information, we can calculate coverage, and we can set up monitoring on that. In certain cases, we want coverage to be very high, and in some cases we want coverage to be low. For example, we do not want urgent data flow to see too much activity, because that means something is wrong. Next, end-to-end freshness. we always had very good tools for capturing latency of individual steps in Dataflow. By putting all those data sets and data pipelines as vertices and edges in the graph, it's very easy to calculate end-to-end freshness, because that reduces to a graph problem. Given a data set as of today, we can figure out all the data stores in which this data lives and all the steps which are involved in making sure that data is making there. We calculate the latencies of that. We produce this neat dashboard and also output end-to-end latency so that users don't have to worry about, but in case they do, they also have this. That completes my talk. My final message is that IoT data is quite unique in many ways. And although you can apply the patterns that we apply in conventional systems, but there will be some edge cases which require first principle-based thinking. And once you apply that, once you sit back and look at the problem holistically, you can come up with very simple solutions which give you a very good operational and observability hold on these data pipelines. I hope you were able to learn something new or interesting today. If you have any questions, I'd be happy to answer them if we meet. Thank you so much.